Meghan Funke. She is a limnologist, and she is with Emmons Olivier Resources. She is going to look at water reuse, retrofitting last century technology for the future. So, welcome.
All right, thank you all for being here.
It's always good for me.
So this is going to be a talk kind of expanding on Brett Emmons' talk earlier this morning, kind of focusing in on stormwater harvest and use as a low-impact development practice. So we're just going to talk specifically about that. Titled it Retrofitting Last Century Technology for the Future. The reason we say that is harvesting water and using it is a common practice globally. We've forgotten about it a little in the U.S., where potable water is available everywhere and convenient. We like having very high quality water for all of our needs, even though it's not always necessary. But in other parts of the world, especially when there are arid climates or water resources are limited, or in poor regions of the world where extracting groundwater is too expensive, this is a really common practice. So we're rediscovering it in the U.S., and I just wanted to define what we mean by stormwater harvest and use. So mainly when we talk about harvesting water, it's anything from rainwater, stormwater across the landscape, even wastewater. We started a little early, so I apologize for just coming in. So definition of harvest and use, right? So we're harvesting rainwater and stormwater, and then we're using it for all of our needs. So irrigation, toilet flushing, wash water, industrial water. So it's kind of the big universe that we're talking about. But specifically in this talk, it's mainly focused on stormwater harvesting and then using for irrigation. So this practice is becoming more prevalent primarily due to three driving factors. One, there are new stormwater rules. This is similar to what Brett was talking about in terms of achieving a zero discharge community. So there's a need, instead of just having rate control, to actually reduce runoff volume. So infiltration doesn't always get you there, so you need an alternative practice. And then there's also some growing concerns with having sustainable water supplies. So our increased growth, population growth, and water demands have depleted our aquifers. This is really obvious. It's a hidden issue because we don't see our aquifers, but at least in the Southwest, the reservoir levels are at record lows. And even in Minnesota, in the Minneapolis-St. Paul region, the suburban cities primarily draw their potable water from the Prairie du Chien aquifer. And it's been in the news a lot lately. We're seeing some low levels in that aquifer that's connected to some larger deep lakes that have shown at the surface what these losses are. The bottom image on the left is just showing large lake level declines in White Bear Lake. And then the top image is showing, so then we're starting to think what's going to happen to our aquifer levels if we continue using potable water from that aquifer. And so the red is showing up to 50% loss in that aquifer level by 2030 with projected growth, and the dark blue is up to 30 to 50 feet of loss of that aquifer. And for that large area, that's a lot of water. And then the third factor is just this, what I would term this energy-water nexus. So what we mean by that is our current system of potable water management, stormwater management, wastewater. It's all very compartmentalized. It's all very linear. So in terms of stormwater management, we have all these costs to handle, collect, treat, and discharge stormwater downstream. So we're trying to get rid of that as quickly as possible. But then on the same hand, after paying for all those stormwater management costs, then we go back and we're extracting groundwater, we're pumping it to a centralized location, we're treating it, and then we distribute it to all our homes. So what if we try to break that linear way of thinking and start to close the loop where we utilize some of that wastewater, stormwater for some of our water demands and save a lot of money in terms of cash, but also environmental costs and energy costs. So as cities and watersheds are trying to meet these new volume control standards, A lot of the cities were coming up with wanting to use stormwater harvest and use for low impact development when they're in these problem sites. So infiltration isn't feasible. They have tight soils, it's close to the groundwater level, there might be some contamination. And so at least we're finding in Minnesota and nationally that this practice is becoming more common. But as people are trying to use this practice to achieve these volume reduction goals, we had a lot of people coming to us asking, well, how much volume runoff does it remove? How much credit can I get for this practice? So we realized there's a need for a tool to help account for this. It's a much more variable system than some of the other practices. So we worked with the Minnehaha Creek Watershed District and Mississippi River Watershed Management Organization to develop a calculator tool to help designers model their stormwater harvest and use systems, optimize storage, irrigation potential, and to really get a sense of what is the percent of volume reduction from their site, how many pollutants or what's the fraction of pollutants they can reduce. So the goal was to have a relatively simple tool. There are existing tools out there if you're familiar with some rainwater harvesting calculators, but they were primarily developed for arid regions where the goal is really to conserve water. They want to hoard it to save it for potable water uses. In the Midwest, where water is more plentiful and we have excess stormwater, our goal is really how can we consume as much stormwater as possible. We want to collect as much stormwater and apply it for irrigation or other indoor demands to get rid of that stormwater. So the tool, some of the key elements of this tool that we developed is it's on a daily basis, which most of these models are, because timing of rainfall is really important. So if you get a bunch of back-to-back rainfall events and you have a pond or a cistern collecting your stormwater, how often you get a rainfall event is just as important as how big your rainfall events are. And then also we wanted to look at not only volume in that system, but also pollutants. What sort of phosphorus reductions and especially dissolved phosphorus can we remove as part of the system? So the kind of the skeleton and the basis of the model is just a water and a phosphorus mass balance. So there's a watershed runoff generator component, so you wouldn't have to figure out what your watershed volumes are and phosphorus flows are. Just use the curve number, percent impervious area to estimate from your site what that watershed runoff volume and load is of phosphorus. And this is particularly related to phosphorus, but in the future could be applied to nitrogen when that's more of a concern. And then within the actual storage itself, this is showing an example of, it could be either a stormwater pond or a cistern. Then it looks at, your dead pool storage, your variable storage, the total size of the basin, keeps track of all of those components of the flow. In addition to evaporation, maybe from the surface of a stormwater pond, the volume going to irrigation, and to overflow. On the phosphorus side, we wanted to keep track of the mixing and sedimentation processes. Stormwater ponds are built to retain some particulate phosphorus, but then also we really wanted to keep track of that dissolved phosphorus pool as it's going out in overflow and then also to irrigation. So in terms of the model setup, it's simplified. It assumes it's one site. There's one storage area. There's your percent impervious area. You have your pervious area, which is assumed to be what you irrigate. But you can always think that, and we've been finding, you can use this tool to simulate maybe you're collecting your stormwater from a highly urban site, but you're going to irrigate somewhere else. So you just put all those numbers into the model. So I'm just going to run through an example to show you what the tool looks like and how it can be used to evaluate the benefits of stormwater harvesting use. So Benel St. Margaret is a private high school in Minnesota. Series of buildings, there's some ball fields, and this comes up better than I thought. So there's black and pink hashing, that's all the impervious area on the site. So the impervious area is 31 acres. And then the ball fields are in the center. There's 2 ball fields and then a track and field. And that's about 8 acres of impervious area that we wanted to irrigate. So the system is modeling, collecting the watershed runoff generated from the 31 acres. There's 2 ponds, one below the track and field in blue hatching. hatching and one below kind of a darker field near the bottom. Those are our storage ponds, and it's used to apply for irrigation water on those 3 fields. I think it's 30% or 38% impervious area. So the tool is trying to be graphical and as simple as we could in terms of input so that water resource managers can use it, but it can still be used for designing these systems. So it just goes through, you have your irrigation, you can set how much you want to irrigate, especially in harvest and use when the goal is to consume as much water as possible. You might want to see increase that irrigation amount as much as possible. How much can the grass and soil really take up? We're not trying to irrigate as little as possible to keep our grass growing. It's kind of the opposite of our typical lawn management of let's dump as much as we can on to reduce our water. In terms of the watershed, that's where you put in, your total watershed area, the percent impervious, some curve number estimates to get your watershed runoff volumes and loads. And then there's all the storage components of your pond or your cistern. What's the volume? What's your dead storage? It gets that evaporation from the pond, which will be variable with depth, since that lower volume is a much smaller surface area. So it accounts for all of those variable factors to really help calculate where that volume is going and what benefit is from that irrigation component. So then kind of the guts of the calculator is there's a graphical output of the results. What I just want to show you, this is 1 year. On the x-axis is just January to December. On the left axis is just the volume in your basin. And so you can see there's a dashed line, gray dashed line on the bottom. That's essentially your bed storage. So we won't ever draw our basin below that amount. We need some volume in the pond or the cistern to allow for phosphorus sedimentation. We don't want to disrupt all the particles as we're pumping out for irrigation. The top line is then our overflow volume, so it would never exceed that amount in volume. And then the blue line is just showing, based on a simulated year with actual rainfall events, what the volume in that basin is. So you can see it starts out about half full, it fills up with a rainfall event, there's some irrigation demand, you see the volume drops, and continues on. So this is useful for designers when you might have existing stormwater ponds, or it might be in a residential area, and it's an aesthetic feature. So there's other things to consider. Maybe you don't want your pond empty all the time because people want to see it as a pond. So you can make sure that it's not always at the dead pool level. And then another thing in terms of sizing is you want to make sure you're kind of optimizing how much overflow you have. So the red bars on the bottom are showing when we have overflow. So we've got a rain event that collected too much water that our basin can handle. And you can see how often that happens and how much. So if you want to try to minimize the amount of overflow, maybe you make your storage size larger. And then just overall, calculate on an annual basis. So from this example site, 31 acres, 38% impervious, it also partitions where that phosphorus in the volume is going. So the phosphorus is in the top bar graph, the volume is in the bottom bar graph. And it's blue is overflow, green is irrigation, and then the orange, especially for phosphorus only, is that sedimentation within essentially your stormwater pond. So it kind of gets at the compartmentalizing. The tool goes through a dry, average, wet year, and then just looks at all 3 years together. But overall, for this site, you can see that if it was just a conventional stormwater pond, we get 50% reduction of phosphorus, mainly just the sedimentation of that particulate fraction. With reuse, we can increase that to 80% because we're getting at that dissolved phosphorus fraction that's going through irrigation and being applied on that lawn instead of being discharged downstream. In terms of volume reduction, maybe 3% with a conventional system where it's just focusing on rate control. We get up to 62% with a stormwater harvest and reuse system from the evapotranspiration from the irrigation. So we really can increase the amount of volume we reduce and also the nutrients, especially the dissolved pool. So just another example how this can be utilized, and this is actually a system that we're designing, and it's in construction right now, is an example of how you can also use this to divert drainage that's going to a downstream impaired water body. So Brant Lake is impaired, it's in the top left corner, so we're taking a portion of the neighborhood, diverting drainage to a storage pond and using it for irrigation of a ball field to help achieve those phosphorus load reductions to improve the water quality of that lake. So overall, just things to think about with stormwater harvest and use as a particular low-impact development tool. One of the great things about it is it's an opportunity to repurpose wet ponds to really maximize the volume and nutrient reduction benefits of existing stormwater detention ponds. I think that was a question that came up in Brett's talk earlier is, that seems great, this was a site that was being developed, but what about already fully developed sites that, have this infrastructure? Well, here's a case you can go back to these sites, look at the existing ponds, and use that water for irrigation to really maximize your stormwater management. Again, it's another tool for achieving those stormwater volume control standards, especially in those problem sites. So when there's contamination of really tight soils and infiltration just really isn't feasible because we're really focusing on that evapotranspiration, that soil absorption through that irrigation component. Removes dissolved nutrients, not many practices do, so that's another focus. And again, it just gets at addressing this overuse of potable water supply. So instead of discharging our storm water downstream and then using potable water for irrigation, can we somehow have that be a circular system? So then I have time, one of the things I wanted to walk through is then we use this calculator tool to just kind of go through a lot of scenarios to figure out, where, how do you optimize your storage in terms of how big you want to make your pond or your cistern, which is what costs a lot of money and you might have limited area, with the need to achieve these aggressive stormwater reduction goals. So where is that balance between the cost benefit versus the volume reduction? So there's going to be a series of 3 figures. I'll walk you through these. The top is a site that's 85% impervious. So this would be an ultra-urban setting. The middle one is 65% impervious, so maybe a single-family home, residential neighborhood. The bottom is 30% impervious, so think of it as maybe a more natural setting, some sort of park. On the left, on the y-axis, we're just showing the annual total reduction. In this case, this is all volume reduction of the system. So then we could, for these 3 test sites, we could change the storage size. So on the x-axis, we're just showing how our storage unit is sized compared to like the depth of rainfall on the site. So there's the dashed lines are showing a storage unit that holds 1 inch of volume of runoff from the site, 2 inches and 2.5 inches, just to kind of get perspective on how big that storage unit is. And then all the different lines and symbols, there's 3 lines showing volume reduction due to irrigation versus evaporation and then total. So you can kind of just look at the top line, which is the total volume reduction. So guys, if we look at these 3 sites, what you can see is when we're in the ultra-urban setting looking at the volume reduction, the line levels off at 1 inch for your stormwater or your storage basin size. So what's happening there, and then as you increase your storage, you're not seeing any additional benefit in volume reduction. And that's essentially when we're using it as an enclosed site, you only have 15% of pervious area, so you're just really limited by your irrigation area. It's kind of a, well, of course that would happen, but it just helps in terms of planning. When you're in an ultra-urban setting, there just should be this understanding that harvest and use is really great, but you're going to have a lot more stormwater runoff that you're collecting. You might need to partner with a nearby catchment, kind of think more regional stormwater management to irrigate maybe an off-site green space, and to think of it in more of a community stormwater management focus and then instead of individual sites. You can see when you move to the 65% impervious site, now we're seeing our volume reduction benefits level off once we get to capturing that 2-inch rainfall event. We're kind of being able to have a larger storage basin size. We're able to collect more stormwater runoff, and then we have more irrigation area in that same site to utilize. Once we get up to the very natural site, you can see we can achieve a lot of volume reduction, even up to getting close to that 3-inch rainfall event. So here, you just have tons of area to irrigate with. So this is, again, combining two sites that might be ultra-urban, kind of nearby natural setting can really maximize that volume reduction. Little animation, help you see that. This figure then is showing those same scenarios, but instead focusing on the phosphorus reduction. So again, the top line is showing the total phosphorus reduction, and the other two are showing the sedimentation, which is the middle line, and the irrigation, which would be that dissolved fraction primarily. So again, in that ultra-urban site, we get maybe up to 60% reduction. So it's just a little bit better than an existing stormwater pond. As we have more area to irrigate, we get up to over 80% reduction in total phosphorus. And in the really natural site, you can almost remove all of your phosphorus, both total and dissolved. You have very little overflow downstream. So again, this is where retrofitting existing ponds is a good idea. So as this practice is coming into use more frequently, there's obvious concerns. So if we're irrigating these natural areas, what kind of water quality we have in that stormwater? It's not potable water. Is there anything in it we should be aware of so we don't have any health risks? And then we can also bring it inside and use it for indoor uses. So nationally and also in Minnesota, there's a strong focus on better quantifying what those health risks are, having better codes so that when cities and watershed agencies want to use this tool, they know what criteria they need to meet and there's clear steps. Minnesota right now is updating their stormwater manual to incorporate these new changes, so there's better documentation for how watershed managers and cities go about implementing this tool. Again, I think there needs to be more focus on quantifying those nutrient reduction benefits. We looked at phosphorus, but nitrogen is also a really important nutrient, as is sediment. And then again, there's just this uncertainty of how much you can irrigate. So really pushing that envelope on, waterlogging tolerance of plants and figuring out the most you can put in that soil and to maximize that benefit of irrigation use. So again, this was conducted in partnership with the Minnehaha Creek Watershed District, the Mississippi Watershed Management Organization. The calculator tool is available on the Minnehaha Creek Watershed site. It's in the top. You can also email me for the link if you want to see what it looks like. And then that Watershed District has a lot more information about it on that same webpage. So with that, I can take questions.
Hey, are there any questions?
I did not understand the slide for that and overflow.
Yes. This side? Or I'm sorry, hold on. That one.
Yeah.
Okay. So this is showing what's happening in this stormwater pond, the storage component of the stormwater harvest and use system. So the blue line is the water levels changing over time. So it's just modeling on a daily time step. It's seeing, is there rainfall? Does the rainfall exceed the storage capacity? If it does, there's overflow. It'll store water. Sometimes there's evaporation losses. So even if you don't have any irrigation, you might see. Are you wondering why the line's going below?
So you're just saying where there's a red line coming off.
Yes, those are the overflow events. So the question is on the overflow events, the red bars, some are much higher than the others. So that's just the size of the rainfall event. So maybe it was a 5-inch rainfall event, and so that might be that highest red bar. So you had a lot of overflow on that day. Go ahead.
Assuming that there's higher operation and maintenance costs from procuring water from a non-potable source, potable irrigation water, at least in my little area, is relatively cheap. So have you analyzed or have an understanding of the cost versus this type of system?
No, and I think that's a good question that's being raised. And now that more systems are put in place, there's going to be case studies highlighted in this Minnesota Stormwater Manual update that's really going to look at those costs. And I think as these systems are established and we're able to track those operation and maintenance costs, there'll be I think, a good thing for us to look at to highlight. Some of the systems are, especially when we bring it indoors, I'm not as certain with irrigation, but there are a lot of companies that are developing the systems, and I think the maintenance on those systems are not as much as you would expect, but there is a cost associated with that, and hopefully as we move forward, we'll better quantify that to help address those concerns. Go ahead.
You also use digital the individual methods of being stormwater or focus on for like I said, like an area and like looking at their stormwater, like on individual
So I'm going to repeat what I thought you said. Are you saying the scale of what we're monitoring?
Scaled down. It's just like an individual house.
So yes, this tool could be, so the question was, can this be used to look at just an individual house? And the answer is yes. So you could just use your area from a rooftop with maybe just irrigating on, you know, the lawn itself. It would be a little harder. The purpose of this is really larger scale, so more stormwater management than on individual lawn basis. And there are some more rainwater harvesters that might be more appropriate for a rain barrel size storage unit compared to these. The sedimentation would make sense in like a rain barrel, but that's a good question.
I'm wondering if you looked at, something interesting to look at would be if this is mainly being used to irrigate ball fields, soccer fields, whatever. Those are usually heavily fertilized, and there is phosphorus. Likely there's a source of nitrogen as well. It could be nutrient recycling as well.
That's a good question. So the question is, if we're irrigating on a site that's heavily fertilized, is there any just runoff from the field?
No, I guess what I'm saying is you could potentially.
I'm sorry, fertilize with the.
Reducing their fertilization costs by irrigating with water that has phosphorus and nitrogen in it.
Right, so she was bringing up the point that for people that may not have heard, that the stormwater can be a replacement for the fertilizer. You're absolutely right. And I think that's why these tools we need these tools to better figure out how much phosphorus is in that irrigation water and adding nitrogen to it as well.